Of a bicycle. Biking is a sport that's been around for years, decades, centuries even. As a sport, there's races, time trials, lots of stuff. Who can get up the hill the fastest? What we have here is an example of a more modern bike. We've got suspension, brakes, gears, chain, all that kind of fancy stuff. You can get a little light on the back for when it's dark out. That's not part of the bike though, it's just there for when it's broken. Bikes have been around for so long, there has to have been improvements that came along the way. Bikes started a long time ago with a German baron named Karl von Dreh. Now, what he invented was nothing near what this is. It was called the Velocipede or something like that. It was probably in German, so I likely wouldn't be able to pronounce it properly. The Velocipede was similar to today's bike, but you'd have the pedals, instead of being here, kind of near the middle and the bottom of the bike, they're fixed to the front tire here. The front wheel, sorry. And instead of being able to hit a bump and compress the suspension, like that, it was a solid frame. No suspension, nothing. You didn't have a comfy seat like this thing, or rubber tires. It was just an entirely steel frame, completely uncomfortable. You hit a bump, the shock would be so much that it could break your back even. Now, I'm not sure on their ability to turn. It looked like they were able to, but you never know. A lot of these drawings of them are very old, considering the year that they were invented in the Velocipede. The design of it was improved greatly over the years. So your initial problem with a Velocipede is that it's all made of steel, including the wheels here. So what we have today for wheels are rubber tires. Now mine are a bit worn out because I've been mistreating this bike for quite some time, but what the rubber does essentially, from my basic knowledge, is that if you look at this concrete floor, you can see lots of little indentations, and it's uneven, right? So let's think about this. If you have rubber is soft, rubber is malleable. You can bend it, you can shape it, whatever form you want, right? That means that when it's being pressed against that concrete, it is going to fill in the gaps much better than steel would. So just grab a random metal object that I had lying around. Pretty sure it's aluminum, but whatever. Probably not. I have no idea. Don't quote me on that. So we take this piece of metal, we're going to press it against the ground, drag it along, at very little resistance. Kind of scratched it up there, so I won't do that again. But it doesn't fill in the cracks. So the steel, if you think about it on a much smaller scale, it's just a little bit of the surface area of that steel is touching the ground. And a lot more of the surface area of this tire is touching the ground than that of the steel. So if I try to move the tire, it's much harder to move. This is because of something called static friction. You've probably heard the word friction before. If you know what friction is, that's the force working against something that's moving. So this thing moving, it's experiencing friction. What it's experiencing is kinetic friction. The difference between static friction and kinetic friction is quite simple, actually. So static friction is the friction being applied to something that's not moving. We have this little dish here, not moving. Static friction, now it's kinetic friction, now it's back to static. The threshold from which it becomes static to kinetic friction is known as max static friction. So static friction is what you want in a bike. So if we look at the bike, the tire's moving, we can see that they aren't sliding. They are still experiencing static friction. Now that might not make sense because while the tires are moving, they should be kinetic friction, right? Wrong. Something has to be sliding, like that, to be under kinetic friction. So when you get to the max static friction of a bike, I think someone's coming to my garage soon, so I might have to cut this. The max static friction, it starts to slide, which is not what you want. So our modern tires are made of rubber to utilize a higher max static friction to prevent sliding, which would happen a lot more with those old steel wheels. So part of the evolution of the bike involved increasing the max static friction. So the next major bit of a bike that we've advanced into is, well, obviously we've got, I'm gonna just touch again on this friction stuff, oils and bearings. So in our tires now, or our wheels, sorry, we've got bearings, which, quick explanation is just, all it is it's a joint that allows rotation with very, very little friction, which is very good for bikes, because that way you don't have to work as hard. We'll be touching on work very soon. But especially with joints, like for the turning of a bike, less friction, much easier to turn compared to maybe a Velocipede would have had no oil, so you would have, if it rusted, it would have been garbage. You would have had to work very hard to turn that wheel. Static friction would have been very high compared to what it is now with the oil, preventing that static friction from getting so hot. What I want to touch on now is the suspension here. So, we all know what suspension does, right? If you're going, you're going to hit a bump eventually, right? There's no such thing as a perfectly flat surface unless you're on a road. Those are pretty nice, though. So you can see, probably can't see it because I'm not going very fast, and I can't get very fast in this garage here, but when you hit a bump, that suspension compresses. You can see the wearing away at the paint and such from the compression itself. I don't even know if that's paint or stains, but the reason it does this is because when you hit a bump like this, you get a wave going through the bike upwards. So imagine you're sitting on this bike, the wave is going to hit that front tire, it's going to travel up through the frame of the bike, straight into your back, and that hurts a lot. So on the old Velocipede, or like an old bike, you'd be pretty injured. Like you could even have a broken back if you're going super fast and hit a bump like that. You get sent flying sometimes too, even with these nice modern day bikes, because they don't have rear suspension, some of them, like mine. But this suspension is very special. So you get something called a longitudinal wave. Now, there's a longitudinal wave. Why is it called that? Because there's another wave called the transverse wave. A transverse wave is something you see in sound. So a transverse wave, here, we got a string here. It goes parallel to a surface. So you see it going like that. See that? Along. It's like the waves in an ocean if you look at it from the side. That's the same kind of wave a sound wave is. That's not what we're concerned with though. So it goes up and down and up and down. We're looking at a longitudinal one. This one goes straight up through the bike. What the suspension does is there's usually a spring or something. When you hit a bump, the spring compresses, right? So that's actually the word for it. It's the scientific word, compression. When it compresses, the wave is traveling through there. So all the force from hitting the bump, you're going so fast, your weight collides with the bump. Now there's an applied force pushing way up on you. That force is going to be much less than it normally would with suspension. The reason for that is it compresses the force into a smaller area. It's got a wavelength, so you don't get all the force in one big shock. Normally, without suspension, you have the wavelength of the wave would be very small. So you'd have it push all the way up really quickly, and it goes straight in your back, and you'd hurt yourself. With suspension, what it does is it slows down the rate that force is traveling, kind of. It doesn't necessarily slow it, but it spreads out the amount of time that the force is being applied. So if you had, let's say 50 newtons of force, that's just a measurement for force. Let's take 50 for example. Without suspension, it's just going to go straight up into your back. We'll just pretend there's no such thing as other things sucking the force out. All the force is just going straight up into your back. But with suspension, it spreads that force out over time. So it's still the same amount of energy, it's just spread out over a longer period of time. And it's called a period in a wave. So the period is a longer period of time. So instead of having a short wavelength, which is another part of a wave, wavelength is how long it takes from the wave to get from where it starts at the middle of the wave, which is called the equilibrium. It goes down below, back to the equilibrium, above, back to the equilibrium. That's one full wavelength. So it'd be much shorter than without suspension, which means all the force of that wave would be put straight into your back, very quick, increasing risk for injury, compared to now, which makes the wavelength much longer, spreads it out over time, which lowers the amount of force going into your back at once. Still the same amount of energy, just over a longer period of time, so it doesn't shock you as much. Your back can take that lower force much better. Lots of garbage in there, eh? It's just meant to spread the force out over time, not to make it less energetic. Still just as much energy in that bump. It's just spread out over time so you don't experience as much pain and force. So the applied force coming from that bump spread out over time. Because the wave going through the spring compresses the spring, which makes it a longer wave because it's going through a denser medium, kind of. So a spring is also made of steel, for example, like the bike would be made of steel. But because of the way the spring is built, it essentially just makes the wave think, let's quote think, it's going into a denser medium. That's not true, waves don't think. But for the sake of simplicity, we'll just say that. Makes it think it's going through a denser medium, so it compresses a lot easier. It's more malleable. That's a better word. It's easier for it to travel through that medium, and it's a lot slower. Essentially, modern suspension, very great, prevents you from breaking your back when you hit a bump. The third and final thing I wanted to touch on, energy. This is a very important one. So with the old bike, the old Velocipede, you'd be sitting on your bike here. Right now I got pedals right there. You'd be like in a very uncomfortable position on that old thing. Though I'll pull up a picture. Well, I would have done it before now while I'm editing this, but you'd be having your feet there. Very uncomfortable way to sit. You'd have a much higher likelihood of falling over, because think about how much time it takes to pull your feet off there, put them to the side here. A little bit more, not much, but it would make a difference. So you're pedaling along with your feet on the front, and you gotta stop. You can't already, that's a problem. Brakes, another good part. Don't know if I'll touch on them though, just to keep this under a 20-minute video. We have something called gears. A chain. These are a more modern introduction. These were introduced by someone else. And what they do is they allow you to, one, have your feet in a much more comfortable position, and two, have, well, rear-wheel drive. I'm not going to touch on that because I don't actually understand the physics of rear-wheel drive. I'm not competent on explaining that, but essentially what this does is you can see we have much bigger gears here at the front and the back. So I'm going to cut this while I flip the bike over. I've just gone through all the trouble of flipping my bike over, only to discover that it's broken right now. The gear shifter is not working, which is wonderful. It's just about time for a replacement anyway. I've been mistreating it for far too long. There was a kickstand there. I fell off while I was biking through the countryside once. But that's not a story for right now. Right now, we're going to focus on, like I said, the gears. So, we all know what energy is, right? It can do stuff. Energy is something that will always exist, cannot be destroyed, cannot be created. That's the law of conservation of energy right there. So energy, there's a couple parts of the law. Energy can be transformed, but you can't create it. You can't just create energy out of thin air. With nuclear energy, uranium always contains that ability to boil the water into steam and spin turbines to make turbines, not turbines, not the one, you know, that you wear on your head, to make energy. So that ability has always existed. It's always been in that uranium ore, or the enriched uranium, I suppose, to do that. Like with coal, it's always got the potential to be burnt and then converted to energy. Although we shouldn't really be burning coal to make energy, it's not very clean. One of the potential forms of energy, like I said, coal has the potential to be burnt to form energy, therefore it's a potential energy. Anyway, I'm getting distracted by my bike being in poor condition here. Another form of potential energy is the one that exists in my muscles, and I suppose my liver. So your muscles and your liver, I'm pretty sure, don't quote me on that, are the two biggest storage sites of sugar in your body. Sugar is one of the forms of potential energy in your body, and through some biology processes, it is converted to something that your cells can use for power. You're made of cells, so it's a potential energy. It's chemical potential energy, because it's a chemical inside your body that can be converted into kinetic energy. Kinetic energy is the energy that my hand is producing by moving. So I hit something, I'm transforming that kinetic energy into a little bit of heat, only a little bit, thermal energy. That's what it's called, thermal energy. And more kinetic energy. So the other kinetic energy it's making is obviously moving this here carpet. It's kind of moving the whole trailer a bit, and it's producing sound waves. That's how I'm speaking right now. Some of that kinetic energy is formed into kinetic energy flowing through the air, because the air exists, right? The kinetic energy is dispersed into the air, which creates a wave. Like I said, this one's a transverse wave, which is what we know as a sound wave. And it travels fairly quickly. Given that it's close to 0 degrees outside, it'll be traveling at 331.4 meters per second. But not exactly, because there's a lot more factors than just temperature. But since we have this potential energy in our muscles that we can convert to actual kinetic energy, we can use that kinetic energy to push these gears, and this is how we propel the bike. A bike is one of the most efficient vehicles out there. That truck there, not nearly as efficient as this bike. It wastes a lot of energy with sound and heat. We don't create much sound when we're biking. Think, when you're biking, the most sound you could create is like groaning in pain if you've biked too much and your muscles hurt. Maybe the sound from hitting the metal parts together, but it's very efficient. The bike is very, very efficient. that's probably why it's not working as well on my bike. I just noticed that sticker. The bikes are very efficient. That's the whole point here. The majority of your energy is converted into that kinetic energy. A little bit is converted into heat, which is the reason why you start sweating and you feel hot when you're biking or when you're exercising a lot. Is because, again, you're not 100% efficient. Nothing is. Some of that stuff is converted into heat, but the majority is converted into the kinetic energy to spin these tires and not to properly shift the gears because it isn't working. Luckily, I can still show you. So we're pedaling, and the bike is being moved forward. Pretend it's not upside down, pretend it's moving down the road, you're sitting on it, you're pedaling, and the bike is moving forward. As the bike moves forward, you notice that you got the gear shifters. So imagine you got this gear here. The front gear is a lot larger than the smallest back gear. Now, if you can imagine two discs spinning next to each other, one is twice the radius of the other. If you measure halfway through the radius of the large one, that point of the radius will be spinning at the exact same speed as the other disc. So, look, if we had a tire half the radius of this one, if we look at spinning on the exact same speed, the tire that is half the radius of this one will be spinning at the exact same speed as the point that I'm pointing at right now, halfway through this one's radius. This one's spinning a lot faster. That's just because of the fact that the end is going to move faster. So if you think about a whip, the end of the whip cracks because it breaks the sound barrier because it's moving so fast. This thing, the tip of it is moving a lot faster than the part that I'm holding, as you can see. This is this chunk of cardboard I found on the ground. Don't know why there's garbage on the floor, but see, the tip moves a lot faster than the part I'm holding. So let the garbage where it belongs instead of being on the floor. The recycling, I mean. The reason that a lot of the higher gears, when you're on these front ones, they're a lot larger. These ones are smaller. It's a lot harder to push. You have to use a lot more energy. These ones are used if you want to go really, really fast. So if you're looking to get to in the middle of the country roads, there's no cars, you just want to zip really fast. Like my dad's got a road bike over there. That's what he uses for races. He can get going really quick, especially down hills, because he gets the help of gravity. But the energy in his muscles is converted. So he uses a lot more of that chemical potential energy to propel himself much faster. This is because you are spinning this gear at the front more. So think, this is the larger one, right? You're spinning this, and it's going pretty quick to spin one of these small ones. And those small ones are going to spin a lot faster. So if you imagine it's connected directly to that small one there from the biggest one. As I was saying, it's connected to the small one from the biggest one. You are spinning this one at, say, I don't know, say the edge, if you're measuring it here, is moving at, this probably isn't a very good idea, but 3 meters a second. That's probably really insanely fast. I'm not going to worry about converting it now, but 3 meters a second, that means that if this was, for instance, 3 times larger, then the other one would be at, also 3 meters a second. But if the smaller one had a larger gear attached to the outside, like the radius, the outside here at this point from the center is spinning at 3 meters a second on this one. It is hooked up with the chain, for the sake of the example, to this one, which is also spinning the outside of its radius at 3 meters a second. But if it had if you looked at the same area from the center of that gear, as right here, so the same distance, it would be spinning 9 times as faster or something like that. I'm not going to do the math, but the point is that it spins the smaller one a lot faster because of the conversion, which is why when you're on a big gear at the front and a small one at the back, it's a lot harder to accelerate. So for those of you who have ridden bikes, you know what I'm talking about. If you're just not moving on your bike and you go from the absolute highest gear, it is a lot harder to get moving because of the fact that you have to produce a lot more energy to move, which is one of the reasons that it works at higher speeds, because you don't have to pedal these nearly as fast at high speeds, because it's going to be amplified, right? The speed of that bottom one is going to be more than the speed of this one because of the whole surface area and the radius thing. It's likely something that you learn in grade 12 physics, or maybe we already did and I don't know it, but all you need to know is that when you go from a big one to a small one, you use a lot more energy to go a lot faster, which is why you don't need to pedal these as fast, but you still need to use lots of energy because you're pushing against these as hard as you can, but the friction's so high that you can only get them moving a little bit. That way when you get to higher speeds, you don't have to pedal super duper duper fast like on a low gear, because that way you'd be at risk of hurting your legs. You just pedal nice like that, and you're not going super fast with your pedals because The gears, they aren't doing the work for you, but they're converting your energy into energy that goes into the ground. Now, if you got a small one at the front here and a big one at the back, that basically does the opposite, where you have to pedal super fast if you want to go really fast. Because, again, small one here, it's spinning fairly slow, and it's spinning this one a lot slower. So the conversion there is the opposite. I'm not going to go into depth with that, because just imagine it does the exact opposite, which is why you'd like to do that if you're pulling something, or if you're going up a hill, because it's a lot easier to get your force to the ground at a lower speed. And it's a lot easier to convert that chemical energy in your muscles and use work, because you're combining that with gravity too. You're going up a hill, so you have a lot more work to do, especially if you're going uphill. You have less if you're going downhill. So if you're going uphill, you got more work to do, because you got the force of gravity and your own, obviously, having to move up the hill, energy, having to go up there, chemical energy in your muscles. You're working up against the hill on a low gear, being converted into chemical energy into these pedals, through the crankshafts, into the actual gears here, through the chain, all the way to the back, into the back tire, which then is translated all the way up through here, into this tire here, which uses its static friction to propel you up that hill. And then you go back down the hill, you're on a higher gear now, you're not working against gravity, you're utilizing gravity to your own advantage. You're now going down the hill much faster, so you're on a higher gear. You have to spin these much less fast to get going fast. All that force is being translated down into static friction. It becomes kinetic sometimes. If you pull your back brakes, it becomes kinetic because it stops the tire, but your bike doesn't stop completely moving because of Newton's law. An object will remain in motion unless acted on by another force. That's inertia. So it can't stop instantly, because if it did, you would go flying, and you're part of the bike's system. So it won't stop instantly. Instead, the back tire will simply slide along the ground. Yeah, that's just about it there. I've dragged this on for something like 15 minutes now. I don't honestly think I'll be showing this in class because of how long it is. So, this is, hope you enjoy watching it. I don't know how much I'm going to edit out, because I spent literally the entire time talking about some of the concepts I was hoping to touch on. I don't understand lots of the other ones. I want to say again, the gears especially, that was one that I had to figure out myself. I actually just did a couple tests with discs. I decided not to show those on the video because they make it a lot longer. I'm sure you could visualize the whole disc thing itself with the radius and it's spinning fast, blah blah blah. Lots of long stuff to explain. Very interesting stuff. I'm going to send you a couple of the articles that I read through for the history of the bicycle. I'm going to put those in with my very loose script that I read over once before recording this and then went completely from memory. That was just so I could organize my thoughts, really. But yes, the whole history of the bicycle, all that kind of stuff. We've evolved in our technology over the years, which has allowed us to create much more advanced stuff. At one point, apparently tires were actually wrapping made of cloth, which makes more sense than steel if you think about it, because obviously, like I said, it's more malleable. It can fill in the cracks in the surface better, and therefore higher static friction, so you get more traction. But it's a very interesting one. There's lots of parts about a bike that have existed forever, like the whole idea of the frame being solid. Then there's parts that are fairly new, like a chain, this whole idea of shifting gears. Very interesting history of the most efficient vehicle known to mankind, as far as I know. I mean, technically more efficient could just be a wheel going down a hill that you're not even putting work into, but that's another story. Yeah, that's the bicycle, and a couple of basic, well, at least 3 basic concepts from physics, explained very simply so that anyone can understand them.